This section deals with an intrinsic centrifugal acceleration I called AIC. And this is the acceleration that eliminates necessity for dark matter. And it's one of the things that actually verifies many of the assumptions of the model, that velocity along the unobserved dimension being the square root of 2 times the speed of light, that this motion is occurring, that the expansion of space is uniform. And so it's a pretty fun, it helps verify and prove the model to be consistent. It also results in making the model conform to observation in terms of the galaxies and where they are located over the course of time. Now, this following diagram kind of illustrates the process. If we have, let's say, a series of points here in the past, and we imagine them moving in this direction, and they are expanded, then all these points are all experiencing a change in their direction. Okay, so this is a kind of a flatland, edge-on view of this kind of proposed model. Now, what this diagram illustrates, if I can kind of include the whole thing in the diagram here. Let's say we have an object, and this object is moving at a very high speed, the square root of 2 times the speed of light, in this unobserved dimension. And while it is in motion along an unobserved dimension, it is also being deflected because it's expanding. So we end up with where basically this is so fast and the expansion is so slow, like it would take over 10 to billion years for the distance to double. So it's a very slow, this velocity is very slow, and this is very fast, so these two lengths are basically the same. And then if we redraw this over here, we can impart this or describe it as a kind of centrifugal kind of a relationship, where here's the velocity in the unobserved dimension, here's the velocity of expansion, and this is a right angle, and we can describe this as establishing a radius, which is also equivalent to the same radius over here because of how close they are and being isosceles relationships. And so based on this, we can, in proportional triangles, we can establish the following relationship, that the AIC, this acceleration from the curvature, is going to be the VU squared over R. Okay, you have a velocity as being conformed to an orbit. So then if we proceed to follow through the relationships, we have that the velocity of expansion is that AIC is equal to velocity of expansion divided by an interval of time. And what's interesting is when you, by proportional triangles, is that the speed of light is no longer a part of the relationships anymore. That the centrifugal type based acceleration is strictly the velocity of expansion divided by an interval of time. So it's all because of the nature of like this triangle is proportional to this triangle, and when you go through the geometry of it, it gives you a nice simple relationship of what the value of AIC should be. And the only thing is, though, that this AIC is a vector projection from a 4-dimensional space. And we have to translate it to our 2-dimensional space. So I thought about this a little bit. And to kind of explain, whoops, sorry about that. To explain this, let's say we have an initial vector, and it's a square root of 2 in terms of its length. Its projection of this vector into two dimensions that are perpendicular to are perpendicular, of which this is within, would have a unit measure of 1. So there is a reduction of the vector when projected along one dimension of the square root of 2 less. Similarly, if we continue this kind of dimensional reduction of a vector from 4-dimensional, let's say in 3-dimensional space, along 1-dimensional space, we can see here that a vector dimension of the square root of 3 would have a vector dimension of each face within a 3-dimensional space of 1. So there's a corresponding reduction. So here a vector in plane mapped to 2 spatial dimensions with a diagonal length with 2 unit perpendicular measurements. We had the square root of 2 is 1 over 1. Then we did with 3, we ended up with the square root of 3. This one we have the square root of 4, which equals 2. So basically what is happening is in a four-dimensional space, is this has a vector measure of 2. The projection of it along one of the 3 spatial dimensions would have a projection of just 1. So if AIC has a measure of 2, its units of acceleration, the actual mapping of it to within 3 spatial dimensions would be 1/2 that. So that reduces the magnitude of the acceleration by 1/2. At least that's how I would believe it works. Now, this next section is the theoretical value of AIC. Let's stop it here.